Good afternoon.
Hello, how are you?
Good. What about you?
I'm doing well. Very busy. This is the end of the semester and everything is happening this week. Like you have projects, I have projects too. So it's, yes, this is the most busy week, I think it has been.
Yeah.
Are you guys going home for Thanksgiving?
Nope.
Yeah, we don't go either. I mean, we are not, our children are not coming because they are in California. And there are so many cases of the virus they have there and in Texas. So they told they have stopped flying from California to other states because when you have back, you have to stay at home for 2 weeks or something. I don't know. They have limited that. So Thanksgiving is gonna be just me and my husband for the first time. It's not gonna be a family event.
At least it's always good to have video calling now being such a normal thing.
I know, isn't it? But you know, I mean, I have to tell you, I have Zoom meetings for all of my work. And when it comes to have Zoom meetings to see my children and grandchildren, it makes it a little too much. It feels a little too much, you know, really. So I was thinking, not another Zoom, you know. But what else can you do? We have not seen our granddaughter for a year right now, if you can believe that. And we have 2 more grandchildren coming this year.
Make it up for next Thanksgiving.
I know, they say it's gonna be a whole, you know, I am of the baby boom generation. I don't know whether you know that, but everybody who was born right after the war until I think late 50s, they call the baby boom generation because there was a boom. There was like a peak in births, in babies at the time.
In my country, yes, it was.
Yeah, in your country it was the same?
In my country, 1950s has a wave of baby boom because the anti-Japanese war and the Civil War has ended. So there might be, but
always after a war. So now it's gonna be after the virus. It's gonna be seriously. There is gonna be a whole generation of babies that are gonna be born in 21 and 22.
I think my country has the largest wave of baby boom in like 1960s.
What is your country?
China.
China. Yeah. Really? Why is it the 60s?
Because, I mean, 1950s is a wave, but 1960s is another wave. Yeah.
Why was it in the 60s though?
Because it's after the 3 years of hardship in China, the Great Leap Forward.
Yes. Yeah, that's what happens, you know. It is always very interesting to see how socially, you know, we make progress over time, and history plays a key role in all of this. But in any case, going back to our own problems, I should not say they are not problems. What I wanted to do today is, I hope we are learning in this class. I know that what we left for last, and I hope we've spent enough time. I'm not suggesting that, you know, we could spend definitely more, because amplifiers is a whole area of study. But what we meant to do is to get a sense and then do some design of amplifiers. I like other things too, not necessarily to become an expert so you can go out and say, now I'm a low noise amplifier designer. That requires a lot more practice. And hopefully you will have that, whether it's in a company, if you decide to go that direction, or whether it is in graduate school for those who want to go there. But at least you have a sense of what it means. And then not only that, but it gives us an opportunity to work not with made up examples. All of the examples we are doing in this class are examples that people have done in practice, and they've used them to develop amplifiers. So we are doing the real thing right now. And you know, it is complex because in reality, nothing is simple, but at least we will learn the process. And when you go out there, you will have the vocabulary to be able to communicate with people on this topic, as well as know enough if you want to learn more, obviously, and learn more and become an expert in that, then you will have an opportunity, knowing more or less of what it is, to get into those more advanced studies or more practice. Okay, what I wanted to do now, considering that conceptually, the design of an amplifier is not difficult, because practically is the design of an input matching network and an output matching network. That's all to it. If anybody tells you what is an amplifier design, you will tell them the design of two matching networks in the beginning and at the output of the amplifier, in the input and output. Now, what gets to become more complex is how you put all of the various specifications, and then you mix them together to be able to achieve as best as you can the characteristics of the desired amplifier. That's where it gets complex. It's not complex, if you like, conceptually, but the steps are multiple, all right? And then there are these small things that you need to have in mind, because one step may lead to another, So it's like a very complex recipe that you will have to follow it very carefully. But in any case, we, because of that, we are going through these multiple times. And what I decided to do in this document, and first of all, I have to take the time and thank 3 students who really helped me identify important typos here and there that needed to be corrected. I have corrected those typos, and if you go on, I updated the files, all the files as of yesterday evening. Now, I'm working on the last document, which is what I have in front of me, and that I will upload this evening together with, I have prepared the videos for lectures of this week. So this evening, these notes I have in front of me, plus the 2 videos Monday and Wednesday, will be uploaded. And then by Sunday, I will upload today's lecture. Now, I wanted to tell you that this afternoon I have to make a presentation for a project which is funded by the National Science Foundation, and they've asked me to get on a Zoom. There is a whole workshop that is going on, and I have to make a presentation so after our class. So I'm not going to be able to have the office hours for today. However, on Sunday, from 3 to 5, 2 hours, I'm going to do a review. And I will send you I will enter the link into the same place where you find the links on eCampus for our class and office hours. I will enter the link for Sunday. It's going to be from 3 to 5. Do the best you can. We're going to record it, obviously. It's going to be a review. I'm going to take the processes that I have put in place, which we are going to go through today, and then I'm going to solve problems on Sunday. Monday, we'll do filters. And then I will have some extra hours of review before the final. We'll talk about those on Monday. And Monday, we are going to have office hours too, and I will do a review there. Okay. Now, last thing I would like to tell you, because I promised, I was trying to get an understanding on your grades where you are. However, the TA is going to finish, and I will finish the grading of all of your homeworks plus the project this weekend. And because he's in the process of entering the grades, I could not get you an exact number. The one that I have is that with the homeworks, I expect, without the bonuses, obviously, but with the homeworks graded and with the final, without the bonuses, the total that we will accumulate, the total, would have been 3,700 and something. I estimated. So 3,730, say, approximately. It might be slightly different than that. It might be 37 or 3,800 something, or 3,700, but about that. And but we still have 1,200 points that have not been entered into the grading. So I looked at the grade distribution, and it looks good in my mind, but I will be able to tell you more in detail of that on Monday, where all of these have, at least the things that are outstanding for review, will be graded, and the grades will enter into the database. I did not want to give you more than that because it may confuse you and may upset you if you have not, if your grades have not entered, we have not entered your grades, and then you think that something is going wrong and so forth. That's why I did not want to come with more details, because it's still out there under development, the whole picture in terms of, but I have to tell you, I'm happy with the distribution of the class. I'm happy with the way the students are working. And so I don't have any other specific comments at this point. Okay, let me then talk about, this is a review document. It's the approach for the design of an LNA. And I'm trying also to divide by this blue line, so you know where one section stops, the other starts. So when somebody gives us an LNA, the first thing we do is stability check. Now, if obviously the LNA, as it says here in the A1, if somebody gives us a transistor, and get prepared for that, because I may give you a transistor that has S12 to be 0 for the final. I may do this because it's going to be easy to do stuff. All right, so be prepared for this. If anybody gives you a transistor where they say specifically S12 is 0, then you know immediately that this is a unilateral transistor. And what does it say here? It says here that this transistor is unconditionally stable. Okay, it says that. So in most practical cases, transistors that have been made, nobody's going to give you an S12 equals 0. They will probably give you an S12 that is very small. So my advice to you is to start at the stability check. And why is that? You're going to tell me, why do you not check for whether you can make this transistor? You can assume it's unilateral. Now, I'll tell you why. Because if I find that my transistor is not unconditionally stable, then I know it cannot be unilateral. If I find a transistor, I repeat, if I find a transistor that is not unconditionally stable, then I know for sure that it cannot be assumed to be unilateral. Do you understand why I'm making this statement? Because if I assume that is unilateral, then it's gonna be unconditionally stable, and that is in contradiction to what I have already found from these formulas up here. Okay. So first of all, let's try to check for stability. These are the formulas for stability. These are correct. I have tested them many times. I want to thank these 3 students, and I gave them a bonus, as I suggested, who helped me find these errors, the typos. And so we take those, and what do we want to find? K, whether K is higher than 1, and magnitude of delta less than 1. And why is this important? Because these two conditions make the transistor unconditionally stable. In most cases, as people say, K is going to be less than 1. In most cases, it's not your delta that is going to create a problem for you, but is your K. But in any case, you need both of them to exist simultaneously. Okay. If I find that my, now here, if I find that my transistor is unconditionally stable, now there is an opportunity that I can assume that is unilateral. And why do you think it will be beneficial for me after I find that the transistor is unconditionally stable? Why is it a good thing to find out whether I can assume that is unilateral? Why do you think that's the case? Who is going to tell me?
It just simplifies a whole bunch of calculations.
Yes, yes, yes. It simplifies all kinds of different calculations, and therefore that's to your benefit. Who wants to have to do so many calculations and then the probability of an error increases? Okay, now let's assume that you are in this situation where you want to see whether you can make the assumption of whether it's unilateral. Now, in that case, we introduce this unilateral figure of merit, all right, here. And you can prove that this unilateral figure of merit is calculated from the scattering parameters like that. The moment you calculate it, then you find out that the ratio of the approximate, let me take, if you were, what this ratio tells you, what this inequality tells you here, it tells you that if I were to assume that my transistor was a unilateral transistor, then my transducer gain will be an approximate gain, all right? So the G sub TA means, like I say up here, G sub TA is nothing else but G sub T under the approximation that is unilateral, okay? Now, and G sub T will be the real value of G sub T under the approximation that is not unilateral, I mean, whatever it is. So if I were to make that approximation, then I found that the error that I make, which I express this error as a ratio, I find this ratio is bound between an upper bound and a lower bound. And if then, as you will see later, I translate that into dB, so I multiply all 3 parts of this inequality by 10 logarithm, then of the entities, then I will find exactly how much error I make.
Sorry, say what?
Excuse me?
Oh, good.
Are you talking to me?
Yeah, I won't be eating rice when I get here.
Okay, can you guys mute yourselves? All of you? All right.
Pardon? To mute
Somebody's
or unmute?
Mute because I hear noise. Okay, unmute only if you want to speak with me or ask me a question. Okay, now So that is going to tell you whether you can do this. We will see a case where we will test that, but this is an important testing. Now let's assume that,
question.
yes, question.
What is the acceptable error range?
Yes, half a dB.
Half a dB.
Half a dB up and down.
Okay.
Plus or minus half a dB. So if this 1 over 1 minus u to the second is about half a dB, and whatever then equivalent is the other one, that is going to be from a half a dB and less. It's a good approximation then.
Thank you.
Okay.
Yes, are those? Oh, sorry. Go ahead.
No, you go ahead.
Okay. So on that equation, Minsky roughly the inequality. Are those? Is it the same unilateral figure on both denominators, or are they different somehow?
Yes. No, it's it looks similar. It's me writing. I'm sorry. I have. There is something there.
Okay.
Yeah. Okay.
That seems odd because wouldn't that be the same number on both sides then? Or
no, it will not be the same number on both sides.
Okay.
One number is gonna be positive on the upper side.
Oh, sorry.
Yeah,
I didn't see the plus and the minus somehow. Sorry.
Okay.
Can I ask a quick question?
Yes.
So you said that the range is a half a dB. Is that a hard limit, or if I say
not the range, not which range? The error is half a dB.
Sorry, that's what I meant. Like the acceptable error is half a dB. But say, for example, I had 0.7 dB, but I can design my amplifier to provide 0.7 dB more gain than the minimum. Is that something I could do, or am I getting into trouble there?
Okay, 0.7 again. So maybe when you go down to 0.7 dB, which is your F min, then if the person who is designing the system, so then you have to follow the requirements of your system designer. All right. Now, if your system designer comes to you and you are the amplifier designer, comes and says, design for me a good, low noise, high gain amplifier. And then we'll give you some other, usually they will give you the VSWR as we talked, because they don't want high reflection at the ports. Then if it's down 0.7 dBs, you will need to ask this person, usually in the specs, they will tell you how much error you need to do. So usually when they give you specs for design, they will tell you noise 4 dBs plus or minus something, okay? Or 2 dBs plus or minus something. They will give you that range of error, because in design, you never find one number, all right? Now you know. In a design, you find a space from where you should select. And for you, who are the designer, to select that one frequency and one matching point for each of the matching networks, you will make a decision, but you are going to be in a space to help you make the right decision. They will limit your space by giving you the errors of their designs, all right? So if they give you a 0.7 dB, a minimum error transistor, low noise, and then they tell you plus or minus 0.2 dBs, then it becomes more strict. So they will tell you. The same thing, they will tell you again, plus or minus some dBs for error. Or they will tell you a VSWR less than to something. They will give you that error in your design to help you. Otherwise, if they don't, you have to ask them. Say how much error, exactly the way you asked me. Is that like, is it half a dB too large? A lot of times, as a matter of fact, engineers who are designing the components are the people who save the day, because at the system level, when you start putting a lot of components together, it's much easier to make an error when you define the specifications for each component. It's the person who is in charge of the component development that can come back and say, you know, if I do this, this is what is going to happen. And then practically you help this person who is the system designer to correct the design. All right. So it's like a very interesting iterative method. And a lot of times, the designers is like artists, but in a constrained environment. So I was thinking the other day, it's like I'm teaching you the palette right now and some techniques on how to draw. But at the end, when you design an amplifier, especially with experience and time, there are so many things that you can do that the best design comes out of people who do follow some process, but then they create beyond that. So practice and experience and interest and all of this. Why am I telling you this is because we learn some rules, but the better you understand the rules and the more experience you get, the better you're gonna be in using them, knowing that you will always at the end be responsible for making an interesting design. The most innovative designs do not follow those rules. They're totally new in a new space. But we're not doing that. We're not going there. I just wanted to tell you that don't think that this is a boring job. As a matter of fact, now as I'm telling you, I'm teaching you the palette, the colors, how to mix them. I mean, you know how boring that can be if you want to become an artist, to start learning the colors and at the same time you want to start painting. We are not in the painting yet, but that's where you can go. Can be very interesting. Okay, any more questions on this? All right, let's talk about conditional stability. Now, let's assume that we found that our transistor is conditionally stable. Now I have to pay attention to something that I'm going to help you with because I saw the questions you're having. What do we do when we want to find the stability areas? We design the input and the output stability circles. Okay, you've seen this. This is the input stability circle, and usually we call that, when we plot it, the gamma S plane. Why do we call them the gamma S plane? Because all of the points depicted on this plane are gamma S points. They have a magnitude, like a gamma reflection coefficient, and a phase. And how do we measure the magnitude? The way that we would measure the magnitude of gamma, like for example, and let's assume you wanna, it's better to show the reverse where you plot a gamma on the Smith chart as opposed to reading its characteristics. But it could be too, like say, for example, let me ask you this, and I will do it on this Smith chart. What if I were to tell you, go and find this gamma S prime, which is 0.630. No, in fact, excuse me. This is what I was not supposed to do. This is what I'm giving you. We know how to do that. Let's assume that I go on this Smith chart and I put this point here. And I want you to tell me how much is the gamma S associated with that point. How are you going to find it? Who is going to tell me? Let me call that. Yes, tell me.
To origin.
So you are want me to draw a line, a red line like this, through that, okay? Point. And then what? Oops. Okay, I did that. Then tell me what?
You can make a circle to find the intersect with the X, the
okay,
x-axis.
I'll make a circle.
Or you can just find the magnitude of the distance.
Yeah,
between...
I'll make a circle because here I cannot find it. So wait, if you wait with me, I'll do it. And so that I don't mix it, I'll make it like that. All right, can you still see it? It's like dotted line. Can you see it?
Yeah.
Okay, then what do I do next?
Draw a perpendicular line from the intersect of the circle with the x-axis. Yeah.
Okay, let me fix it. Somewhere there, I will put that, also same style. Okay, then what else?
You can see the magnitude from the ruler.
Okay, let me read the magnitude. Let me fix it. And I will do the same thing here. All right, and that is about, say, point. I'll write the magnitude first. Is point what? Could you read it for me?
It's not lyric here.
It looks like 0.78.
Yes. Point, oops. Ah. Okay. Sometimes notability complaints. Okay. 0.78. Okay. Now, what else do we need to do?
Phase.
Phase. How are we gonna find the phase?
From the line you drew.
Yes, I got the line there. And then where am I going to read from?
The reflection coefficient.
Yes, so I'm gonna read from here. There. How much is that?
Ooh. 109.
Okay. 109. Because we measure exactly, yeah, it's the reflection coefficient, which is 109. Ah. Okay, so every point on this Smith chart is going to give us a gamma S. So we selected that arbitrarily, we found the value, okay? Now, we call it a gamma S plane for that. And in this particular case, we drew this center, this circle, let's assume, all right, I gave you the example here. And the circle is, no, the circle is this. I gave it to you as an example. Does not necessarily correspond to any particular transistor. I just gave it to you. Okay. Now, we know that. How are we going to find where is the stable region? I have put it here, but tell me how are we going to find it, and where is not a stable region? How are we going to do this? It says here that if S22 is less than 1 in outside of the circle of the white in the blue area, that's the stable region. How do we find this out? Because really, what do we have in here? It's a gamma S, all right? This is the plane. And let me include here, underneath it, one page, so I can write. Okay, how are we going to find out that the blue area is the stable region? The true condition, which in fact I will put here for you on the left, because it's not contradicting what I have, it's just a condition too in a different form. The condition here is that gamma in that's what the condition is, or gamma S in that particular case. That gamma S, well, is less than 1. Gamma in is less than 1. The condition is that gamma in is less than 1. Now, how much is gamma in? From the expressions, where did I have the expressions? If I don't have them here, I'll find them for you. Wait. What second? We have seen them. I just need to find them where I have listed them. Okay. Did I say gamma? Wait a second. One moment. Make sure that I give it to you accurately. 1 second. I'm gonna find gamma in. Okay. For this case, let me write, I'm gonna write them. I'm gonna write the expressions where I have, that's why I'm looking at these equations. 1 moment for gamma in. Okay, here they are. I will write them for you so you have them next to this. Okay. What we need here is S22 to be less than 1, but in reality, the condition comes from the following. From gamma out is less than 1. Why is it gamma out? Remember that the amplifier has 3 pieces: the transistor, the matching network out, the matching network in. They are connected. And here is gamma in, here is gamma out, here is gamma L, here is gamma S, okay? Now, gamma S has to be equal if we go for complex conjugate matching for highest possible gain. Gamma S will be equal to gamma in complex conjugate. Okay, gamma S is less than 1 here because gamma S is already inside the Smith chart. So magnitude of gamma S is less than 1. But gamma in is a function, and gamma in is going to be less than 1. But then when you go at the output port, your gamma out is not independent of your gamma S. Your gamma out, and I'm going to write it here, is given by the following relationship. And you will find it in your notes, is equal plus S 1, 2 gamma S 1 minus S11 gamma S. And that we want to be less than 1. Okay, now that we have that, what do you see here? You see that your gamma out, since your gamma out is going to become equal to gamma L complex conjugate for maximum gain, if we want to get there, then your gamma out, it has to be less than 1. So your gamma S influences your gamma out. And if your transistor, your amplifier is to be stable, then your gamma S needs to be in a region that will make your gamma out also less than 1. not only gamma S less than 1, which is already the case because we are on the Smith chart. Now, how are we going to find gamma out? We go to the center of the Smith chart. We look at the place at the space that incorporates the center of the Smith chart. And it's this one. If I were to choose that point, how much would my gamma S be at that point? Let's assume that I choose this point. How much the gamma S is there?
That's at center?
Yeah.
0?
0. So at the center, gamma S is 0. Okay, let's see what happens when gamma S is 0. When gamma S is 0, then your gamma out is what? This.
S2, 2.
And that's why S22 has to be equal to 1. So we test this condition always at the center of the Smith chart, and the region that includes the center of the Smith chart is the stable region. Did you get that? That's how we select it. And of course, it's assuming that your S22 is less than 1, obviously, all right? Because if your S22 is higher than 1, it's going to be the other region, unfortunately. It's not going to be the blue. But let's assume now for S22 that you have all of the S22s less than 1. And that's what we have seen. We said that it's very rare that a transistor will have S22 more than 1 for some, I don't know, maybe for a special application, not for this one. Okay, so you always see for those applications we'll do in this class, which space incorporates the center of the Smith chart. And that is your stable region. Did you guys get it?
Yes.
Okay, now following the same, now we say, okay, now I'm saying that in this particular case, the stable region is not the one that incorporates S22, the center of the Smith chart. Because when I go and check at the center of the Smith chart, if I still have this point and check for this point, then this point gives me, that will give me this, which is this, which is that. And therefore, this area that incorporates, in this case, the center of the Smith chart is the unstable region. Okay? Now, same thing with output stability circles. In the only cases there we are looking not at gamma out, but gamma in this case. Okay, and in this case,
for output stability, we're looking at input reflection coefficient.
Yes, because of that, I told you, because the input reflection coefficient affects the gamma out. It's the input reflection coefficient that affects gamma out.
Okay.
Excuse me, is the, what did I say? The output reflection coefficient that is affected by gamma S or gamma, yes, gamma out is not affects gamma S affects gamma out rather. I mean, I understood what I wanted to say. Now, in the other case here, if we go here, then the relationship would have been the following: gamma in, to write both of them on the same.
Is the gamma in equal to complex conjugate of gamma S?
Gamma in is complex conjugate of gamma s only when so gamma in we force it to be. When we want GA maximum, when we want to have the maximum available gain.
Okay.
Now, when you look at the gamma L, at the gamma L plane, you're not concerned about your gamma S anymore. All right, you're concerned about what you have in there and how you select your gamma L. You are in the gamma L plane anymore. What you're thinking is what your choice of gamma L would impact the most. And your choice of gamma L impacts gamma in, according to the relationship that I gave you here. If I select a gamma L, then I impact my gamma in directly. See how I'm thinking? If I select a gamma L, then I do practically finalize the value of gamma in. And that's when then I make gamma S to be gamma in complex conjugate. So it depends on what you want to select first. If I select my gamma S, then I impact gamma out, which if I want to make equal to complex conjugate of gamma L, that practically it fixes my gamma L value. All right, so, but if I select gamma L, and if I choose to make my gamma S equal the complex conjugate of gamma in, that it fixes my gamma S value. But these conditions apply if I choose to design the amplifier to have the maximum available gain, not in every case. And you have seen how we design, not for the maximum available gain. If you have to also satisfy noise conditions, and if you have to satisfy your VSWR conditions, you're not gonna design for maximum available gain, all right? But why is it important to know what is the maximum available gain? So you know how much you compromise. You know how much low you go, what your amplifier can give and how much you get. So in any case, you go now to gamma L, and practically you do here the same. You look at the center of the Smith chart after you drew your line. You look at the center. Let me see one thing I want to see here. Okay, this one has to correct. It was by accident. So this one. Okay. Now, you look again at the center of the Smith chart, and if for that, if S11 is magnitude less than 1, the space that incorporates the center of the Smith chart is your stable region. And if S11 is larger than 1, then the space that incorporates the center of the Smith chart is not your stable region, is the other one. Okay, that's how we select it. Do you understand now that? Because I saw some people who had some questions with the homework. So you had something like this for the homework, or you had, what did you have? You have something like this for the homework, but it was a slice, a thinner slice of blue. And it was the other region that incorporated the point. So practically what you had in your homework, let me do another, sorry. I know I probably got you dizzy already. So let me add here. So in your homework, you had something like that for your Smith chart. and you had an output circle, I think like this. And you wanted to get this one as your stable region. Obviously, in your homework, you had S11 less than 1, so this is your stable region. All right? The stable region in this case is this one. Do you now understand? Yes? No? Tell me.
Is this, so this particular diagram, it's for the output stability circle, right?
Something, yes. Yes.
Okay, and so in that case, you actually, the stability region is within the circle, not outside
Yes.
of it. Is that what you're saying?
Yes.
Okay.
Yes.
Yeah, I think that makes sense to me.
All right. For those who were had some questions. Okay. Now, so you check for stability and you find your, like you did in your homework, you find for the stable place, because you have to be in the stable place to be able to continue with the next. And the rest is going, now that you have found your stable, your stability regions, now you go to find where your gain circles will be, and then your noise circles, and then at the end, your VSWR. So after this, yes.
Would you go to page 8 really quick?
8. Yes.
So
okay.
In this case, the S11 was less than 1 and the stable region was outside the circle.
Yes, because it incorporates the center of the Smith chart. And at the center of the Smith chart, your gamma in here, I will write your gamma here. Your gamma in here at the center of the Smith chart equals this one, S11.
Yeah, I can understand that. But in the example, the Smith chart you just drew, the S11 was less than 1, but you said the inside the circle is the stable region.
Yes. So here is you choose the region that incorporates the center of the circle. If your S11 is less than 1. We chose this, the blue, because that incorporates the center of the Smith chart. We choose this one because this incorporates the center of the Smith chart, and S11 is less than 1.
I see.
Okay?
Okay, thank you.
Okay.
Could you just clarify? So could you say that, like, if S11 is less than 1, you choose the area that incorporates the center, and that's your stability region, and if S11 is not 1, then you choose the region that doesn't incorporate your center?
Yes.
That's the stability region?
Yes.
Okay. Or I should say, yeah, if S11 is greater than 1, then you choose the other way. Okay.
Exactly. Very good. Okay. On Sunday, not office hours today, so I have to give a presentation. On Sunday, 3 to 5, I will send an announcement and I will incorporate on eCampus the link. I mean, yes, the link, so you can click on that and connect. We are going to continue here. And then at the end of this, I have examples. All right, we're going to go through the process, and at the end of this, we'll solve an example. We'll do that on Sunday. We'll have 2 hours, so we'll have more time to finish this and then do the example. Okay?
Okay, so is there a quiz today?
No quiz today.
Okay.
Professor, I have a quick question.
Yes.
Back when you found the gamma S earlier in the lecture, I don't know what slide it was in, but you.
Here.
Yes, it's one more up. Yeah, that page. How did you get that gamma S line? I missed how you drew that line.
The solid line.
Yes.
I measured my gamma. So I want to find C sub S, all right? I want to find this one.
Okay. And so I understand how you found the circle. I just don't know how you drew that line or how you came to that conclusion. Hello?
Professor, you're muted.
Professor, can you hear me?